Good evening, AP Statistics Crammers. I am super excited about tonight. This is probably one of my favorite units that we're going to be talking about tonight. My first year teaching stats, I really didn't like it, and I think it's just because I didn't understand it. And now that I can see how it fits into the mold of everything, I am super excited and super pumped up about this. As you can see from my Bitmoji up there, it's a little bit scary. After I put it in my background, I was looking back at it. I was like, yeah, it's a little bit intimidating. But anyways, so yes, I'm really excited about this one. This is one of my favorite topics in AP Statistics because it takes what we've talked about in the last 4 weeks and it paves the way seamlessly into inference, which is the big deal in AP Statistics. It paves the way for confidence intervals and hypothesis tests. So I'm super excited about that. Always, things are being recorded. Names. Most of you who have been here before have figured that out very well. It's posted on YouTube. The replay's there. I might refer to you by name in the chat. All that good stuff. Socials, make sure you hit us up on Twitter, Instagram, YouTube. Lots of great AP content. Also current event contents to keep up with on all those social media channels. Upcoming things, and you can also see them above. Ooh, I messed up there. On that one, I have the same date. I meant to go back and change it and didn't. This is today. This is where we're at right now. So the Unit 6 crams are... It's actually April 6th at 5 p.m. Eastern. And then tomorrow the trivia is at 9 p.m. So that was correct. And it's also Daylight Savings Time. That's confusing. It's not Eastern Standard Time. It's Eastern Daylight Savings Time. That has already thrown me off a few times over the past few weeks, making that adjustment as well. Okay, so trivia coming up tomorrow night on Unit 5 at 9 o'clock. And then, of course, our 5-hour cram finale. That's where the rubber really hits the road and we prepare for that exam day on the 17th. So I'm super excited about that as well. All right. So in this stream, we're going to look at what is a sampling distribution. I think that might be one of the most important things is just what exactly does it represent. And then once you understand what it represents, I think it makes a lot more sense why we do the inference procedures that we do. What are the conditions for sampling distribution, which also shows up on inference in the next, really the rest of the units that we're going to be covering in our cram season. How do we do sampling distributions for proportions? And how do we do sampling distributions for means? Okay. Oh, you're right. Okay. That is incorrect. My time. The cram is actually at 6 Eastern time. I looked at my calendar, which is in Central time. Man, time zones suck. Time zones suck. So, yes, make sure, which you get emails from Amanda about your cram events. That keeps me on track. And that will be at 6 Eastern time on April 6th. Okay, and I'll remind you of that again at the end because my graphic is wrong and I can't change my graphic without totally deconstructing everything that I've done. So I don't want to do that. So what is a sampling distribution? Okay, so we have two things here. Actually, we have three things, really. So we have a population distribution. That is if you take every individual in our population. Okay, let's say we're talking about AP statistics students, and we take everybody's AP statistics score, okay, their exam score at the end of the course, and we put that on a density curve, a distribution, a 1, 2, 3, 4, 5. That would be our population distribution. Okay, now a sampling distribution is where you take there's kind of a middle piece in here. We'll hold off. So that's what we were just saying. A population distribution is when every individual in our population represents one data point. Okay, again, all AP scores from the 2020 AP statistics testing. So then you have a sample distribution. Okay, not to be confused with a sampling distribution. So a sample distribution is when you take one sample of a given size and you show those values on a curve. Okay, so let's say we take a random sample of 150 AP statistics scores from that testing date in 2020. Okay, so that is a sample distribution. That is 150 individuals on a curve. Okay, population, every single person that took the test. We know that that's probably not likely to be able to really collect in a lot of instances. That's why we use samples and ultimately sampling distributions to determine things. So a sample distribution is one sample of a certain size, 150 in this case. Now here's where the real money comes in. A sampling distribution is when we take every possible sample of a given size and we average that sample to create one data point, and then plot all of those averages on the distribution. So with our AP statistics testing score example here, let's say that we took all of those scores from 2020 from our population and we created every possible sample of size 150. Okay, there's pretty much an infinite amount of possibilities there. Okay, so every sample becomes one data point. So we average up all of those samples. So we have a sample of 150. We take all those 150 scores and average them to create one data point. Okay, and we put that on our curve. And then we do that same thing 150 times because we have, or not 150 times, an infinite amount of times because there's like an infinite amount of ways of creating that sample of 150. And that's where we get our sampling distribution from. Okay, so every unique sample gives us 1 point in a sampling distribution. So basically, we're looking at where does our one sample fit amongst all possible samples. Okay, so I don't think I understood the difference in a sample distribution and a sampling distribution. A sample distribution is one sample, 150 points. Those 150 points individually all make 1 point. A sampling distribution, which is really what we're focused on here, is one sample of 150 translates to one data point, the average of those 150. Then we take a new sample of 150. That becomes the second data point. Then we take another average of 150, and that becomes the next data point, and so on and so forth, until you've done every single possible sample of that given size, 150 in this case. And you can tell there's a change that happens as you go from population, each individual, okay, to a sampling distribution. It becomes more and more, what's the word I'm looking for here? Someone in the chat? Our population distribution does not reflect this, but our sampling distribution does. What happens as we do that? Our sampling distribution looks a lot more blank. Yes, I knew it was coming. It becomes a lot more normal, okay? Which is, as we all know by now in AP statistics, it gives us a awesome curve that we can use rules by to calculate probabilities. There's where that p-value is going to come from when we get to hypothesis tests in 2 weeks, okay? Or a week and a half, actually. I think it's next Saturday. So yeah, we get those p-values because our sampling distribution is normal. Okay, we're really going to bring together that piece of normal distribution from last week, the normal CDF stuff, with a sampling distribution to create our inference. Okay, so it becomes more normal. So there's this really cool tool here. Okay, and I just searched for sampling distribution online stat book. Okay, and this is the link, and it gives you a really awesome tool here to see how sampling distributions work. Okay, I hope I'm not losing audio here, changing scenes on OBS. I think I have that fixed. Okay, so this totally breaks it down just like we were talking about. You have your population distribution, all right, and I can change that, and I will in just a minute. Then you have your sample distribution, so your sample data, and then you can create your sampling distributions, okay? So we're going to watch this. I'm going to change my parent distribution to be like what we had in the slides, okay? Not normal. It's got two little bumps in the data. And I'm going to do this. I'm going to do a sample size of 5. All right, so there's 1, 2, 3, 4, 5, and then 1. Okay, this is my sample distribution. I have 5 dots on my sample distribution. I have 5 data points. Now, so far, my sampling distribution is this 1. I've done 1 sample of 5. The average of those 5 gray dots is this 1 blue dot. Okay, and I can do it again. 1, 2, 3, 4, 5, and there's my second blue dot. Now I have created 2 samples of size 5 based off of this, okay? And it has averaged those 5 to create this blue dot. And I can keep going. You can do this as much as you want, okay? And you see, I'm going to skip ahead here. If I do, so that was doing 1 sample. This is 1 sample of size 5. It gives me 1 dot. So I've done that 3 times. I've pulled three unique samples from my population to create, I'm building my sampling distribution. Now, what you can do to kind of speed things up is instead of animating 1 sample of size 5, I can just do 100,000 at one time. And if I do 100,000 at one time, look at that nice curve there, okay? My parent population is not normal. It's kind of symmetric, but it's surely not normal. And then my sampling distribution, even when my sample size was only 5, looks really normal. Now, what do you think is going to happen if I do the same thing? I'll leave my parent population alone. So I can do a sampling distribution of sample size 5, and also a sampling distribution of sample size 25. So somebody in the chat tell me what's going to be the difference between my 2 sampling distributions. So animated, there's 5, dropped 1, and then, oh, I got to change it to mean. So 2, there's 5 and 1, and now it's going to do 25 and 1. So 25 dots. Takes a while. Those average to be this. So it animated 5 data points, a sample size of 5, and averaged them to go to this blue point. And then it took a sample of 25 and averaged them to be this 1 data point. So if I could repeat that 100,000 times, what's going to be the major difference between this curve of sample size 5 and this curve with the sample size of 25? Somebody in the chat let me know what that's going to be. And then we'll animate it. Okay, y'all are on the right page 100%. Yes, sample size 25 is going to be closer to normal. That is true. The distribution will be a smaller range. I like that. I also like what Priscilla says. It's less spread out. It has less variability, so a lower standard deviation as well. And it's going to appear closer to normal. So let's see how that looks. Okay. Both of them look pretty normal, okay? I think we all could agree with that. That's kind of the definition of a normal curve. If I drew that on my paper, I would be happy with that normal curve. But the sampling distribution of a size 25 is much less spread out, okay? It only goes from here to here, whereas the other one goes almost all the way across the graph. And the scales are the same between these two. And you have a much more shrunk in. And I like somebody said it is more accurate. Remember, the goal with a sample is to estimate what's going on from the population. Normally, we don't really know this, okay? But if our sample size is bigger, it's a better estimate of the population, which is what we're ultimately trying to do. That is what we are getting into, is we are trying to take a sample and we are trying to estimate the population, okay? So that is huge. Now, what's really cool here is I can make this one as funky as possible. Okay, this is about the most abnormal thing I could think about drawing. And if I create that, all right, and this is the one with sample size of 5. There's some issues there, right? It's got a weird little skew to the right here. It's more data on the left, so the tail kind of goes to the right. It looks kind of strange. You can tell there's something going on here. And you can sort of still sell that with a sample size of 25. So I don't want to get ahead of myself here, and I really wish that this app had that option. If we're dealing with quantitative data, in other words, we're dealing with means, what is normally our magic number that we want our sample size to be at least? Somebody throw that in the chat. What is our magic number that we want our sample size to be at least, where we can say, hey, this is normal, we're good? Yes, we need to be at least 30 typically. Okay, so we need to be at least 30. 30 is kind of our magic number. That's kind of where we really want to be at. And if we're at 30, then we're typically, there's a theorem for that tells us that our sampling distribution is going to be approximately normal. It means if we're taking every possible sample, which we can't technically do every possible sample here, but if I do 100,000 samples, it's going to be pretty close. Okay, we're going to get a pretty good idea of what that sampling distribution looks like. So if it's at least 30, we can be pretty sure that that sampling distribution is going to be approximately normal, which just opens up a world of possibilities. If I do, let's see, something really skewed. All right, again, you see a skew with that sample size of 5. Even more so with a sample size of 2. And then as you get more to that larger sample size, it does become more normal. Okay, so it's a really cool tool because you can make your population look like whatever you want, and you can see that normality start to establish itself. I love sharing that. So let me get my stuff pulled back up here. All right. So yeah, that's online stat book. I think I usually search for like sampling distribution applet. I'll put it in the chat actually. That's not that hard. Okay, so yeah, if you want to go play around with that, it's really neat to see that normality kind of come into play there. So when you're given a sampling distribution, there are steps that you need to be able to follow in order to describe that sampling distribution. Now think back to Unit 1 when we were describing distributions. What are the 4 things that is always important when describing any distribution? So put one of them in the chat and we'll see if we can cover all 4 between all of us. Spread, outliers, center, and shape. Okay. Does anybody want to remember the acronym we used for that? There's a few of them that you could use. What they said, that's right. Yes. CUSS! There it is. There's the acronym. So yeah, so whenever you're asked to describe a sampling distribution, you're doing the same thing, okay? You are describing a distribution. You are going to tell what the center of the distribution is. You're going to tell if it has any unusual features. You're going to tell the shape, and you're going to tell the spread, okay? All right, now, so the first thing is, what's the center of the distribution? That's the first part of our CUS, or SOX. I know some of y'all use that, which the unusual features and the outliers, same thing. If I weren't so glued to CUS, I probably would do SOX, because shape is more important in the beginning, so doing that first kind of helps out. So the center of our distribution is either going to be, so if you're dealing with proportions, so if I take a whole lot of proportions and take or a whole lot of samples and take the percentage of each sample, so if I take, I have all high school students and I take a sample size of 50, and I asked everybody, do you like Takis? Okay, yes or no. And I find that for my first sample of 100, 80% like Takis, okay? And then my second sample, 72% like Takis. And I do that for all of my possible samples of size 100. And then I average all those together. I'm going to get the population average, or the population proportion who like Takis. Everybody is being included in the same amount of samples, and it's all dividing out and averaging out. So the middle of my sampling distribution for proportions is going to be the population proportion. So the average of all of my sample proportions is equal to my population proportion. Okay? Same thing goes for means. If I take the average of all of my sample means, I'm going to get the population mean. Because again, every person in the distribution is being included in the same amount of samples and also not included in the same amount of samples. Because a sampling distribution is all possible samples of that given size. So, everybody's being added in. Since you're averaging all those together, you're being added in and not added in the same amount of times. So therefore, it would be the population mean. Okay? What is the spread of our sampling distribution? There are formulas for that. And we know that as that sample size goes up, our population, or our standard deviation for our sampling distribution is going to come down. We mentioned that earlier. As the sample size goes up, the spread or the standard deviation is going to go down. Okay, super important there as well. It's a huge concept. I think that's one of our non-negotiables at the end. And the reason why is because you're dividing by the sample size. If I divide by 100, my number is going to be smaller than if I divide by 10. Same thing over here. Even though it is in the square root sign, that number still, the bigger it is, the smaller the overall answer becomes. Okay, and then for the big one, what is the shape of our sampling distribution? We are typically looking for it to be normal. So if we're dealing with proportions, we're going to use what's called the large counts condition, which verifies that our sampling distribution is approximately normal. Okay, so that's NP greater than or equal to 10, and then N1 minus P greater than or equal to 10. Basically, you're looking to see that you would expect to have at least 10 successes, 10 people who like Takis in every sample, and also 10 people who do not like Takis in every sample. Generally, if your sample size is big enough, that's going to cover that for you. Okay? So that is for proportions if you're dealing with categorical data. Now, if you're dealing with means or quantitative data, you're going to use the central limit theorem. That is, a lot of people call it the fundamental theorem of statistics because it opens up so much with quantitative data for us, which is that the sample size is, as we mentioned earlier, greater than or equal to 30. Okay? So there's one thing that out of our describing distributions that I haven't mentioned so far. Okay? And to be honest, you don't have to mention it with sampling distribution. What is the one part out of the 4 things we typically have to do that I have left out? Yes, okay, so the unusual features, or in other words, mostly the outliers. What about the other three things means, what about the three things that we have discussed tells us that we don't have to worry about outliers when dealing with a sampling distribution? One of those three things sort of answers that question. Yes, the normal distribution. Okay, that never occurred to me like the first few years I taught statistics. I never connected those dots from Unit 1, cussing the data, to sampling distributions when we're describing a sampling distribution. But you're exactly right. Typically, and we can make our sample size large enough to create a normal sampling distribution. Therefore, if we have that normal condition is almost always going to be met. Otherwise, we can't really do much else with the data collection. So if that is in fact a normal sampling distribution, there's no need to look for the outliers. Because if it's normal, one of the definitions of a normal distribution is that it is symmetric, it is unimodal, it is bell-shaped, and there are no outliers. Okay, it follows that nice shape there. Okay, might have an outlier in the population, but our sampling distribution, if it's more than 30, it's not going to have those. It's not going to hurt your score if you have a problem to describe a sampling distribution and you go through cuss the data and you say there are no apparent outliers, especially if you said there's no apparent outliers because we previously stated that the shape was approximately normal. If I were a reader, which I've never been a reader, unfortunately, if I were a reader and read that, I would be like jumping up and down because you've made that connection between why it's important to check for that normal curve in terms of outliers and things like that. So yeah, it's totally the same thing as Unit 1, but our standard deviation is smaller because our sample size is more than 1. And the outlier thing, generally speaking, isn't important because it's covered in the fact that the shape is approximately normal. Okay. I did want to include this. It kind of shows up in sampling distributions, and it is important. When you are estimating a population, you want to be sure that your estimator, whatever you're using, be it mean, median, mode, something like that, and you're trying to use that value from your sample to estimate your population. You want to make sure it has two things. It has a low bias and a low variability. Okay, and you can see here, basically what that means is that you're hitting a bullseye. Okay, so if you have a low biased sample, your sample reflects your population. Therefore, the average from my sample is going to be pretty close to the average from my population. And that's why you can see the two that have low bias, the points are centered around the bullseye that you're trying to hit, okay? Over here, let's go from political spectrum just for ease of, we associate that word bias with politics a lot. So over here, it looks like my sample is more left than my population. So my estimate is going to be biased. It's going to be biased more toward the left of the general population. Here's my general population. All my sample values are left of that because it's biased. I only asked people on the left side of the aisle. Okay? And then you also want to have low variability. Low variability means that the points are clustered together. They're all pretty close to each other. So if they're all pretty close to each other and they're all centered around the bullseye, the population that you're looking for, that would be low bias and low variability. Over here, we don't have variability. They're all pretty close to each other. We don't have them scattered everywhere, but they're not centered around the population, so there's bias. Over here, we're not biased. We got a little bit of everybody, okay? But there's a high variability. Maybe our questions weren't asking precise questions. Okay, so we're getting kind of all over the place. Our questions may not be worded in a way that bring things together. And then obviously high bias and high variability, there's not much you can do with that. Okay, it's scattered and it's not centered around the population or the value we're trying to estimate. So you want to make sure whatever you're using to estimate the population is low variability and low bias. I really like that precision and accuracy. I remember in science class and a lot in my education classes in college talking about creating exams that have good precision and good accuracy. It's not biased towards maybe a certain class of students or a certain group. Culturally, there's bias in exam questions. We know that for sure. You want to make sure things are not biased. Therefore, you're getting an accurate representation of what the students know about the content, not about some cultural reference that doesn't make sense to a certain group of people. And then also it's precise. It is focusing on those standards. It's not focusing on, a little bit on this standard and a little bit on this other standard all the way in left field. You're focusing on precisely the standards you're supposed to be focusing on, the questions on the assessment. And it's the same way with that. Okay? So now, and this is another connection that I just thought was really cool, and this is one of the reasons why I love this chapter, because it takes the stuff from Unit 1 and it takes the stuff from Inference and really brings those together, and it shows how it paves the way. So we have, anytime we're doing inference, we're getting a little bit ahead of ourselves, but it's important here. We have 3 conditions that we have to check before we can perform an inference procedure. Typically speaking, it's a little bit different when you get into chi-squared and regression tests, but 90% of the inference we do in AP statistics hinges on 3 conditions. What are those 3 conditions? Throw those in the chat for me. And I'm going to take a sip of this awesome Rockford peach tea. We have a new tea place in the little small town that I'm in Alabama randomly. It's called Moody Nutrition. They opened up like yesterday, and we went there today. It's pretty tasty. It's a random shout out. If you're in Moody, Alabama, go check out Moody Nutrition. I'm sure that applies to no one. Yes, random, normal, and independent. Okay. Normality, random, independent. A lot of times you'll see it, just the order I normally teach it in, no reason particular, is RIN. And our students kind of pick up on that, that RIN sort of order, I guess, that helps them remember, okay, I'm checking conditions, RIN, and then they go through those. Okay, so those are the things that we need also for a sampling distribution to be accurate. Random is not really there, but if you're basing your sampling distribution off of a non-random sample, you might as well stop there. Okay, you have a biased sample, and a biased sample is not going to do you any good. There's no fancy math that I can do to make sure that to fix that. Okay, you took a biased sample. You only asked your friends who are more on the left side of politics. You're going to get an average that's more left than the general population. Okay, and of course, only asking your friends political questions and trying to make national inference based off of just your Facebook friends, and maybe you saw the video back in the fall that I did for Fiveable. That's just really bad practice. That's not a random sample, in fact, that you're only asking your friends, so you're going to get a biased sample towards your friends, which probably reflects your personal political beliefs, which is just not good. Okay, I experienced a lot of that back in the fall. So what's really cool about these conditions is that they match with those aspects of cussing the data. So the random sample is important because it tells us that our center is unbiased. Okay, we want an unbiased estimator for the center of our sampling distribution. If our samples are randomly chosen, which we know that's important, then our center is accurate. So that formula we had, that the average of our sampling distribution is the population parameter. That is true if our samples are taken randomly. Okay, so random tells us the reason why we need a random sample is that so our sampling distribution is accurately centered where it needs to be to estimate the population. Okay, so random matches with the center part of cussing the data. The next condition is independent, or order really doesn't matter. Okay, and which part of cussing the data is the independence condition going to be important to? Somebody know that in the chat. We've only got two because remember we took out outliers, and center is the random condition. So we got spread and shape. Okay, why is independence important? Which one of those two does it fall in line with? Yes, that has to do with the spread. Okay, because I mean, you know, shape is normal, and that's the other condition. So kind of process elimination there. So we can check that using the 10% condition or the 10% rule, and that is necessary so that that standard deviation formula works. Okay, the mean formula, which is just that it's the population parameter, hinges on the fact that it's a random. Think back to geometry when you're doing proofs. Well, how do you know that the mean of your sampling distribution is the population parameter? Because my sample was random and it's an accurate reflection of the population. Well, how do you know that the standard deviation of your sampling distribution can be found using this formula? Because the 10% condition is met. And we'll talk more about that on into inference. Basically, independence is that one person in the sample is not affected by the other, and you want to make sure that your population is large enough that the population is at least 10 times the sample size. Basically, the reason for that is since our population is 10 times my sample size, that means that when I change my, trying to think of an example here. If we have a 1,000 marbles in a jar and they're numbered 1 to 1,000, and what the probability of me drawing marble number 8 is 1 in 1,000, which is super small. And then I leave that marble out, the first marble I pull out. It's not marble 8. And then I'll pull a second marble out. The odds of getting marble 8 on my second draw is 1 in 999, which is still extremely small. Okay, those probabilities technically did change. So technically those two events, pulling first draw, pulling marble number 8, and second draw, since it's without replacement, is technically they're not independent. But if that 10% condition's met, that my population is at least 10 times my sample, or the way that Sanders written it out in the chat's the inverse of that, then that difference in probability is so negligible, 1 in 1,000 versus 1 in 999, that it's essentially independent. Okay, that difference due to that with sampling without replacement is so negligible that it's essentially independent. Okay, so that impacts our standard deviation. And then, of course, our last condition we have to check is our normal condition. Large counts for proportion or central limit theorem for means. If the central limit theorem is not met, we also could have a normal population distribution. If it tells you that the population is normal, then our sample is going to be normal. Or even if that's not met, a box plot of the sample data showing no skew or outliers will also do it. That's why sometimes that sample size of 5 gave us a sampling distribution that was approximately normal on the little applet we saw earlier. All right, so here's kind of some examples here. We have a uniform distribution. That's where every outcome is equally likely. If I take a sample of 2, it kind of creates a point. If I do a sample size of 5, those points start to mellow out and becomes more curved. Sample size of 12, even more normal. Sample size of 30 looks like a perfectly normal curve. It really kind of rounds out even with sample size of 5, to be honest. I think it shrinks in a little bit at 12. If we have one that's strongly skewed to the right, remember, because our tail is to the right, like an exponential curve would be, a sample size of 2 is not normal. All right, it is still skewed to the right. A sample size of 5, still skewed to the right. You can see how it doesn't match those dotted lines. Actually, let's change scenes here so you can see it a little bit better. There we go. Okay, hopefully that's helping you guys see it a little bit better. So yeah, you can see on the exponential, it really takes getting to 30 before our sampling distribution matches that dotted curve. And then, of course, if you have a normal population, the normal sampling distributions, all it's going to do is shrink things in. But it still follows the normal shape, just with a lower standard deviation. Okay, but all three of them, when the sample size was 30, was approximately normal, because these are all quantitative graphs here. All right. So let's look at what happens with a sampling distribution for a proportion. So here's our question. A landscaper has been planting kale plants for clients for 10 years. We had a fun discussion in the Fiveable Slack today about growing plants, and I was working on these as I was doing a garden last week, so this was fresh on my mind. He has found that about 60% of kale plants will grow and produce edible kale within one season. I'm pretty sure kale is only a one-season plant anyways. So anyways, maybe I should have used some sort of flowers that come back every year. But so 60% of kale plants will grow and produce kale within one season over the course of his 10 years of working. So what the landscaper does is he takes a random sample of 150 kale plants used with clients. All right, so the first thing we want to do is we want to describe the sampling distribution. So what's going to happen if we took all possible samples of size 150 out of all the things he's done over the past 10 years? Okay. All right, so the center of our sampling distribution is going to be 0.6. And again, the reason why is because our sample is randomly selected. Since I'm selecting a random sample of 150, all possible random samples of 150 is going to be what the population is. Every kale plant is being included and not included the same amount of time. So it's all going to average out to be equal to what the population is, which it tells us is 60%. So there's our center. There's our first part of CUS. The spread of our sampling distribution can be found using the standard deviation formula. And the reason why, it's reasonable to believe that a landscaper who does this every day has planted at least 1,500 kale plants in the last 10 years. There's your 10% condition. You also could say that 150 is 10% of the population. You can word it that way. I like taking the sample size and multiplying it by 10 and saying that it's reasonable to believe that the population is at least that. Okay, so kind of going the inverse of 10%, instead doing 10 times my sample size. Instead of 1/10 the population, do 10 times the sample size. That's the way that I have sort of processed it. So the formula, all right, our p-value was, or not p-value, our p was 0.6 based off the problem. Therefore, the complement of that is 0.4. Divided by 150, take the square root of it, is 0.04. So my standard deviation is 0.04. Okay, and then the last thing we have, I ran out of room on the slide here, is our shape. Okay, now this is a proportions problem, so I want to make sure that that we use, since we're doing proportions, we want to use large counts condition. This is not 150 greater than 30. Okay, we need to use our NP greater than 10, 0.6 times 150, that's 90. So we have 90 plants out of our sample. We would expect 90 plants to produce fruit, or produce edible kale. I guess it's not a fruit. And we would also expect there to be 60 plants that didn't produce kale. Yes, square root of some teachers use PQ times PQ over N. I'll go back. The formula sheet words it as P1 minus P, which is Q. Okay, it's the complement of P, divided by 150, which is the sample size. So yes, you're right. That is the formula we use to get our standard deviation. And remember, that formula hinges on that 10% condition. I can't use it if the 10% condition isn't met. Just like I can't say the center of my sampling distribution is 60 if my sample's not random. Okay, if I only take the plants that look dead, well, I'm probably going to get a lower percentage there. All right, so yep, so that is met. We would expect 90 of our 150 to produce kale, and we would expect 60 of them not to produce kale based off the numbers he gave us. Therefore, at least 10 successes and failures. Our shape will be approximately normal. Okay, so that was cussing the data. Again, since we had approximately normal, there's no need to worry about outliers on the cussing the data. Okay, that should be part B. What is the probability that our random sample of 150 yields 85% of plants that will yield kale within one season? What calculator function are we going to use here? It is a very popular calculator function that we use all the time in AP Stats. And it hinges on, yep, Megan's got it, normal CDF. It hinges on that condition we just checked. So since we know that our sampling distribution is approximately normal, we can use normal CDF. And the two things we need for normal CDF is a mean and a standard deviation. We know our mean because it was a random sample. We know our standard deviation because of that independence 10% condition. Okay, the conditions are all giving us this tool. It's opening up that toolbox for us and allowing us to use those tools. All right. Again, we previously verified that it was normal. We can use normal CDF. Our lower limit is 0.85. Our upper limit is a gabillion. Now, technically, we could use 1 here because the highest percentage is going to be 100%. Okay, so 1.00. With a mean of 0.6 based off of our population proportion and a standard deviation of 0.04 based off of that formula that we were just talking about, the PQ over N square root. Okay, and we get, whenever you do that in your calculator, you get essentially 0. All right, you also could have calculated the z-score and used the z-chart. Okay, your z-score here would be observed, which is 0.85, minus expected, 0.6, divided by standard deviation, 0.04, which is 6.25. The likelihood of getting a z-score of 6.25 on an approximately normal curve, pretty much not going to happen. Remember, normal curves go between -3 standard deviations and +3 standard deviations. So getting a z-score of 6.25 is just not going to happen. That's why the probability is essentially 0 there. Okay. Any questions on that before we move on? I'll pause for a minute and then we'll look at means. All right, and you can see I did draw a curve because we should be drawing curves when we do normal CDF, okay? My middle is 0.6, 1 standard deviation, 0.64, 0.68, 0.72, which pretty much covers all of it, and we're all the way over here at 85. It's not gonna really happen there. Yes. The mean of your sampling distribution is your population proportion, since we're dealing with proportional data here. That's on your formula sheet. Let's see, I can go back. All right, So the mean of our sampling distribution is P. So if I take all of my sample proportions and average all my possible sample proportions, I'm going to get my population proportion, okay, because that sample is random. And that I copied and pasted this from the formula sheet packet you will get when you take the exam. If you do it online, have that printed out ready to use. That's definitely one of the resources in an online test I would have. If you're taking the test in person, that will be given to you just like as part of the testing materials. Okay. All right. So let's move on and look at means. A recent data company measured the amount of minutes that teenagers spend on TikTok each day. I would probably be an outlier for my age group. I spend way too much time on TikTok. It's just such a cool app. I don't know. Anyways. The study found that the data was approximately normal, with an average time spent per day was about 111 minutes with a standard deviation of 8.5. So that is my population values. Population mean, population standard deviation. And then it says find the probability of selecting one individual who spends less than 100 minutes on TikTok each day. Okay. I know that my population is normal. This is going back to the last chapter when we talked about probability. I know it's approximately normal, therefore I can go ahead and do normal CDF. Okay, less than 100 minutes, that's negative infinity. I can't remember, Sandra, if you want to put in the chat what you use for those lower and upper limits. I just use really large and really small numbers, either on negative or positive side. Negative 1e, negative 99, and then 1e, positive 99, I think, is the infinity breakdown. So anyways, so lower limit is negative 1 bagillion, okay, whatever. The lower limit, or the upper limit, is 100. Now I should be labeling my calculator speak here. I need to start doing that on our slides more. And then 111 is my mean. Yes, 1e negative 99, 1e positive 99. Good, thank you. And then our standard deviation is 8.5. We're taking one individual. This is not a sampling distribution. This is just a normal probability problem. Okay, and I get about a 9.7% chance. Okay, all right, here's my normal curve. I'm centered at 111, go out 8.5, 8.5, 8.5, to the right, 8.5, 8.5, 8.5. And then that one individual is going to fall right here. Now you could do a z-score. All right, 100 observed, 100 minus expected, 111, divided by 8.5 standard deviation. Okay, gives you a z-score. Then use that z-score with a z-chart score to find that area under the curve with a z-score chart. Blah. Okay. So now what we're looking at, find the probability of selecting a random sample of 80 individuals who spends an average of less than 100 minutes. So before we were finding one person who spent less than 100 minutes on TikTok each day. Now we're going to pick 80 people and we want their average to be less than 100. Okay. Our work that we're showing here is going to look almost the exact same as the last problem. What is the one thing that's going to change in our breakdown? Y'all can throw that in the chat. What's the one thing that's going to change from part A when we're selecting one person to when we're selecting a sample of 80? Exactly. The standard deviation is going to change, okay? Because now we are dividing by that square root of n. Go back to the formula sheet, okay? For quantitative data, for means, we want to use the standard deviation of our population divided by the square root of n. Before we did that pq over n or p1 minus p over n square root. Now we're using the quantitative formula there, which means the standard deviation is getting smaller. So if I had to take my standard deviation, 8.5, divided by the square root of 80, now my standard deviation is less than 1, it's 0.95. So it's significantly smaller. Okay? So now my normal curve does not go out as far anymore. Okay? So negative 1,000 to 100, or 1e negative 99 to 100. That's my upper limit. My mean is 111. Mean is still the same. Still centered at the same number. But now my standard deviation is not 8.5 anymore. Now my standard deviation is 0.95. That comes out to be pretty much 0. All right? It gets much, much smaller. So as our sample size gets larger, my standard deviation gets smaller. Therefore, it's shrinking that curve in. Okay, actually, I have a normal curve on my shirt here. We could have used that earlier. I have a normal distribution and a paranormal distribution. It's a ghost, like a Pac-Man style ghost. But as we increase that sample size, it's going to shrink things in and in. It's going to bring it in more and more. And the more our sample size goes up, the more it hones in directly on that population parameter that we're trying to estimate. It's the whole goal behind statistics. Okay, so then I went ahead and put some context there. The probability of selecting a random sample of 80 teens with an average of less than 100 minutes on TikTok is practically impossible at 0, based off the data we were given from the study. Okay, I would hope that that's possible, but then again, I don't know that I would fall in that sometimes. So yeah, that is what happens. So basically what you could think about this, okay? Going back to part A. All right. Let's go with a lottery scratch-off ticket. The odds of winning the lottery one time, or winning a scratch-off ticket, whatever, is about 9%. Okay? Not great odds, but they're okay. Now we're going over here. That was winning the lottery once. Now we're going over here. What are the odds of winning the lottery or winning a scratch-off ticket, whatever? 80 times. All right, well, it's pretty much impossible. If it's only a 9% chance of it happening one time, well, the chances of it happening 80 times pretty much ain't going to happen. This is how casinos make their money, by the way. You can go into a slot machine and hit the button or pull the lever and win money, okay? But if you pull that slot machine a whole bunch of times, 80 times, the casino is going to make money off of you. Okay, the law of large numbers. They are going to make money in the long run. You might make money in the short run, okay? The only 2 times I've ever been in a casino, I can't remember what the first time was, but the second time I was on a work trip with my principal and one of the other teachers, and they wanted to go in the casino in New Orleans, and we went in and they were like, all right, we'll meet back out here in 30 minutes. And I was like, well, I don't know what to do for 30 minutes. So I went over to the slot machine and put, I think, $10 in, and I was like, if I lose $10, whatever. And I hit the button and it went up to $15. I won like $5. I like hit a miniature jackpot or whatever. And I was like, you know what? I don't want to pay for my coffee and beignets after we leave here at Cafe Du Monde. So I hit cash out, took my little ticket over to the little machine, and it gave me my $15, and I went and sat on a park bench and waited on them to finish losing their money. But if I would have kept playing that slot machine, and I would have played it 80 times, I won that one time, okay, or maybe it was twice, something like that. But if I would have kept playing, eventually my money would have dwindled down and it would have all went to the casino. Because the odds of winning are low, you might win that one time, but the chances of you winning 80 times, it's not going to happen. That's exactly what's going on here. Okay, that's more of a proportions idea. The proportion of people who win, proportion of people who win 80 times is basically nothing. So anyways, that's exactly how casinos get you. That's how they are rich. That's how they have massive buildings that are beautiful and awesome and cool and all colorful and everything, because they're making money off of most of their people. Yes, you're right, Sandra. I have like a lifetime return of 150% at casinos. And I would say I would keep it that way, but, no guarantees. If a casino is in my path in some other time, I might test my luck, and try these theories that I've been sharing with students for so many years. Okay, so if we were to describe this sampling distribution, okay, it is approximately normal, and our sample's more than 30. So actually, this meets our central limit theorem, and our population was normal. So both things are verified. Our sample was selected at random, therefore the middle of our sampling distribution is 111 minutes. Since the 10% condition is met, I kind of gave you my little can statement there. Our standard deviation is 0.95. Okay, so there's my three things. Don't need to do outliers, because if it's approximately normal, it's not going to have outliers. Yes, Sandra, I could write a book about my secrets to success, and it would literally be don't go. You know, that's it. Yeah, don't go to a casino. You want to not lose money at the casino, don't go to a casino. Now there are some games, I guess, that are skill based, blackjack and poker and all that, but I don't know all that. I wanted to go like the movies and hit the slot machine and it make all the colors go off, and it didn't really do that. It was just like, yay, you won $5, and I was like, well, that wasn't very fun. And I was like, I can get coffee and beignets for free, so okay. So yeah, the secrets to a casino is don't go. All right, so our non-negotiables, and we're using this to build up towards our 5-hour cram session. Number one, be able to apply the conditions, random, independent, normal, to describe sampling distribution. Random matches center, independent matches spread, normal matches shape, obviously. Be able to calculate probabilities from sampling distributions for means and proportions. Remember, if it meets the normal check, you can do normal CDF. You can use your mean, because it's a random sample. For your mean, you can use your standard deviation formula, both of them on the formula sheet, for your standard deviation. So again, those conditions match with the normal CDF calculations, match with the cussing the data. It all comes together. This idea here, I promise you it's going to show up. As your sample size goes up, your standard deviation is going to go down. We saw that. That's why that curve sucks in and gets closer and closer to that true population parameter. Be able to verify and differentiate between proportions, being large counts for normal, and means using central limit theorem or a normal population. Also, and we'll get to this in a few weeks, be able to check if we are using, or be able to know if our sampling distribution is with one mean or two means, one proportion or two proportion, which also brings in that combining random variables that we kind of brushed over last week. I realize that we can discuss that and this in the inference chapters, because it is. You're combining two random variables when you're finding the difference between two means or the difference between two proportions. So just kind of prepping you for that inference procedure we're going to get into next week. Is it means or proportions? Is it one mean or two mean, or one proportion, two proportions? And because that affects the type of inference you do. It also affects your formulas for your sampling distribution, and it affects your normal curve, your normal condition, large counts or central limit theorem. Okay, so that's our big five. We're going to be over in Discord taking questions and all that type stuff. So again, I want to remind you, my screen here is incorrect. The next cram is on Tuesday, April 6th at 6 p.m. Eastern, not 5 p.m. Eastern. That is wrong. It is at 6 p.m. Eastern. That's 5 p.m. my time. I goofed there. Also, be sure to check out the trivia tomorrow night on Wednesday, March 31st at 9 o'clock Eastern. Okay? Hope you all have a fantastic week if you're on spring break or not. Hope the weather's as nice as it is for you as it was for me. See y'all next time.